Hey there, everybody. We're going to practice drawing some ray diagrams for circular mirrors today, and along the way kind of talk about the different rays and how they form images in different situations, and run through the calculations of how we calculate exactly where an image is and exactly how high or how tall it is. And so these handouts are in the little handout that I made for you guys. The first page says circular mirrors on the top, and it kind of gives us the directions of what to do. And then this page here is some diagrams for us to draw on. Now this was drawn real careful to scale using a compass. That's why it's not produced in a computer. This radius of this circle actually matches this distance right here because I drew it carefully with a compass. And the numbers are going to be just slightly off because I had to scan and then photocopy this from what I intended. And so if we get a decimal, that's not what I intended, but we're going to go with what we got, so it's accurate. The first thing we're going to do today with this diagram, we're going to look at the concave mirror side first. So concave mirrors are where the open side of the mirror is on the side that the object is on. So we're going to be working in this area to begin with. First thing we're going to do is measure the radius of curvature. And so we're going to grab our ruler and we're going to line it up with that center dot and then measure from the center dot to the edge of the mirror along the principal axis. So this distance right here would represent the center of curvature. That's the radius of the mirror. I meant for it to be 6 centimeters, but it's actually 6.2 after being scanned and photocopied. And so the radius of curvature, we can call that R if you like, is 6.2 centimeters. The focal length of our mirror then is half that. So that would be 1/2 of 6.2, which would be 3.1 centimeters. So remember that the focal length is 1/2 the radius of curvature. And so we're going to grab our ruler and measure from the radius, excuse me, from the center of curvature, halfway between there and the mirror, and we're going to put a dot there. We're going to call that the focal point F. And we can do that same procedure on these other diagrams. They hopefully are to scale. And this one came out about the same. Put a dot right there in the center. There's the focal length. Put a dot right there in the center. There's the focal length. Okay. So we got the center of curvature and the focus of all of our different mirrors plotted. Returning to the directions. In the first situation, we are going to draw an upward arrow 1 centimeter high at a point along the principal axis exactly halfway between the focus and the mirror. So let's grab a different color here. By the way, I'm encouraging you guys to draw this in pencil and then highlight it later on with different colors. I'm going to use colors so that you can see it a little bit better on the screen. We're going to go halfway between the mirror and the focus, so that's going to be just a touch over 1.5. And then we're going to draw a 1 centimeter tall arrow. So actually measure 1 centimeter tall so that our measurements and our calculations sort of line up with each other. And we're going to label that object. You can go OBJ for object if you like. We're going to trace 2 rays to locate the image. The first ray that I always recommend you start with is the ray that starts off parallel to the principal axis from the top of the object. So from the top of the object to the mirror. And then when it reaches the mirror, a parallel ray of light is going to reflect through the focus. So line your ruler up with the focus, and then draw your ray like that. And if you like to keep a label of things, especially if you don't have different colors, maybe call that ray number 1. We need 2 rays in order to locate the image, so I'm going to grab a different color. Let's go with red. Let's draw the second ray. The second ray that I recommend you do is the one that goes to the center. And so the way that we draw this ray is we carefully line our ruler up with the top of the object and the center of the mirror's curvature. We start at the top of the object, we go to the mirror. If you like, you can kind of indicate, hey, the arrow's going that way. But we don't move our ruler yet, because that ray, because it is along a radius, strikes the mirror perpendicular to it, or normal to it rather, and then reflects back through the focus. So the incident angle is 0, so the reflected angle is 0. And so it just reflects straight back through the center. Sorry, I think I said focus. That's going to look something like that, and that would be ray number 2. I would encourage you guys not to move your ruler at that point, because what you're going to notice is that these two rays are not going to cross. They're diverging from each other, and we need them to converge. We need them to meet at one point. So the trick is we extend those rays backwards behind the mirror. So returning our ruler to that ray, and I can't really look above my picture because the camera's right there. So forgive me if I'm just a little bit off due to the parallax. I'm actually about a foot away from this. I'm doing the best I can, y'all. Okay, so there's my ray number 2 extended, and then do the same thing with ray number 1. When you line your ruler up with ray number 1, remember you're lining it up with the ray of light that actually goes to your eyeball, not the original incident ray. Do that. And, you know, make them clean and neat like that. When you draw extended rays, always use a dashed line. So these are dashed lines. If you drew solid lines already, just take your pencil and erase some dashes into it. That works just as well. A lot of times better than trying to dash it ahead of time. Where those rays cross, that is where we're going to see our image. And so line your ruler up with the point where those rays cross and your principal axis. Draw an arrow. It's going to go upwards since they cross above the principal axis, and label that image. Yours may be a little bit off, depending on how careful you drew yours and how careful I drew mine. We'll figure out exactly how careful we were here in just a second. So I'm going to first measure the image distance. That's the distance from the center of the mirror to the spot where I see my image. And so that's going to look like this, and I get like 2.9 when I do that. So SI, image distance, I get 2.9, and of course that would be centimeters. And then the image height, we can measure that with our ruler. When I do that, I get like 1.8, I think. And so this is my image height, HI, 1.8 centimeters. Now on the other handout, the one that's typed, there is a table at the bottom for you to record these things. And so you're going to record your actual measurements. Don't you dare write down my measurements. HI, I got 1.8 centimeters. You're going to write down what you got. And then SI measured, I got 2.9. Okay, so while we're on this, we can go ahead and indicate if this is a real or a virtual image. Since the rays of light do not physically cross, the extended rays cross, that makes it a virtual image. Since the arrow points up and the rays cross above the principal axis, I can say it is upright. So this image is going to be virtual. I'm not going to be able to see it unless I actually look with my eyeball into the mirror. And it's upright. I'm not going to see it upside down. It'll be right side up. Okay, so there's our ray diagram. Now let's actually go and calculate the image distance and the image height. And I've got some space on the handout like right here where we can kind of work through that together. So the equation we're going to use to figure out the calculated image distance, 1 over F equals 1 over SO plus 1 over SI. And so solving for 1 over SI, I get 1 over, subtract 1 over SO from both sides. It would look something like that. You could be fancy and be like, SI is the inverse of that if you wanted to, or you could just like solve for 1 over SI and then flip it at the end. All right, so our focal length, that was the 3.1 centimeters that we calculated earlier. So 1 over 3.1 centimeters minus 1 over SO was half that, and so we put our dot at 1.5 centimeters. And at this point, like those numbers, we're not going to add up nicely. It's okay to grab a calculator for this. So 1 over 3.1 minus 1 over 1.5. You get negative 0.344. 1 over centimeters. And so taking the inverse of that, so just 1 divided by the answer, gives me negative 2.9. for the image distance. And so looking down here, I measured it to be 2.9. That's this distance right here. The negative sign indicates that it is a virtual image. And so if I'm measuring this, like using the actual array diagram to get this, what we kind of got to remember is to go back and say, well, since I had a virtual image, that really should have had a negative sign in front of it. I got to think to do that. Virtual images, the image distance is going to be negative. The image height we can calculate by doing HI over HO equals SI over SO. So multiply both sides by HO. I knew I was doing something wrong there. Okay, so the object height was 1 centimeter. The image distance, let's use our calculated value of negative 2.9. And our object distance was 1.5 centimeters. And I gotta apologize again, I forgot my negative sign up here. So negative HI over HO equals SI over HO, or you put the negative sign over there, it doesn't matter. There should be a negative sign at the beginning of that. And so a negative times a negative is going to give you a positive. Doing 2.9 over 1.5, get something like 1.9 when you do that. Times 1 is 1.9. So down here, my calculated object height was 1.9 centimeters. Go ahead and put in my calculated image distance. So when I drew that, I was off by a millimeter when I measured my image height compared to the calculated image height. Not bad for government work, sitting a foot away from the piece of paper that I'm drawing on, in my opinion anyway. Sorry about the mess up there. So the negative sign is important because we want the sign, our final answer, to indicate whether it's upright or virtual. And so since this is upright, that one right there, I should get a positive image height. So virtual image, negative image distance, positive image height indicates that it is upright. So those numbers jive with what we measured on the diagram. So at this point, what I would encourage you to do is hit the pause button and then do the second example on your own. Then hit the play button. I'm going to work through it quickly. I'm just going to draw the ray diagrams. I'm not going to redo the calculations because I'm going to go ahead and go with you guys can do the math here. Like, math is not what we're working on today. Working on today is really drawing those ray diagrams. So you'll know the math isn't working out for you if your calculated and measured values are way off. And so if you do the ray diagram correctly and you mess up with the math, you should notice it when these numbers aren't close together. They're not going to be exact each time, but they should be close together. So hit the pause button, do number 2, and then hit the play button and see how you did compared to me. Okay, welcome back. Golly, a lot's happened since we last talked. So let's look at situation number 2. We have the same mirror, which means it's got the same center and the same focus as our first mirror up there. This time we are going to draw our object halfway between the focus and the center. So we're just going to slide our object over into this vicinity over there. So let's do that real quick. And it's about 1.5 centimeters in between, and then draw it 1 centimeter tall. Label that object, OBJ for object. So the first ray I would advise you to draw again is the one that starts out parallel. When you do this one, and this is kind of where the error comes in when drawing these things, make sure that your ruler is parallel as possible to that line right there. Goes to the mirror. And then if you can avoid picking your pencil up as you slide your ruler to line it up with the focus, that would be best. And then you want to draw this ray like as far out as you possibly can. Like that. So there's ray number 1. Ray number 2, just lined up with the center rather. So that would look like that. If your ruler doesn't actually meet the drawn mirror, that's okay. You just go ahead and draw it as if it eventually got to the mirror. Even if this ray of light doesn't physically exist, like even if that ray of light didn't actually strike the mirror over here, the reflection would still behave as if it did. And so it goes to the mirror and then reflects straight away from the mirror. A smaller mirror, you would just see less of the image height, like part of it might be cut off if it is a smaller mirror. And so that's where my rays of light are crossing. Let's grab my ruler and let's draw the image. Let's label it image. And then just as a real quick check, let's kind of measure the image distance and the image height real fast. So my image distance in this case is 10.7 centimeters. This is a real image, since the rays of light actually cross, meaning that I should get a positive number for SI. And when you do the math and you calculate SI, you should get a positive answer for that. Measuring the image height, I get 2.5. So HI equals 2.5 centimeters. Now, since that is an upside down image, fancy way to say that would be inverted, I has to remember to make that negative. So when I write down the image height, it needs to have a negative sign in front of it to indicate that it is an inverted image. So after you do the number crunching on that, hopefully we get something in the vicinity of those numbers right there. And hopefully your measured values are reasonably close. I mean, they don't have to be exactly, but hopefully your measured values are pretty close to those values right there. Now hit the pause button and do the third example. Okay, welcome back. Let's get the third example together. The third example, we are going to draw a 1 centimeter high arrow, this time on the other side of the center. So like that's going to go over here. So basically we're going to measure 1.5 centimeters to the left of that center dot. So 1.5 centimeters puts me right there, and then draw a 1 centimeter tall arrow right there. Again, label that object, just like that. So the first ray we can draw, again, goes parallel through the focus. Kind of like that. The second ray would just go straight through the center and then reflect backwards. And again, if the center of the mirror or the mirror itself doesn't extend all the way, that's okay. It's going to act like it did. It's going to go there and then straight back. So it's not the first ray that goes there that we're looking at it, but actually it's reflection. And it crosses the blue ray at that point right there. So that would be the location of my image. That would be a real image because those rays of light actually cross at that location. Please pause while I turn the lights back on. Okay, so that is a real image because the rays of light physically cross, and then because it is upside down, points downward, that is an inverted image. And I will leave it to you to measure your image distance and your your image height. Your image distance should be something between 6 and 3 because it's between the center and the focus. So that'd be an easy one to tell if you made a mistake. Like if you get something greater than 6 or less than 3, that would be over here, over here. Obviously, you've done something wrong. What we're going to do next is move on to convex mirrors. So put those away. Same kind of setup here. I've got some hand-drawn mirror diagrams here. Again, I drew those carefully with a compass. And then some descriptive directions up there. Same thing first. We're going to measure the radius just like we did earlier. So again, line my ruler up with there. And on this one, it's real nice. That lines up exactly with 6. Hooray. So this distance right here R equals 6 centimeters. Except it is a convex mirror. So what that means is that we have to remember to make that negative. -6. It's on the wrong side of the mirror. That makes our focus, remember focus is 1/2 the radius of curvature. 1/2 of 6 would be 3 centimeters. And we need to remember to make it negative when we use it in an equation. So let's go ahead and plot our focus on here. Just exactly halfway between the mirror and the center. That may get a little bit crowded there. Okay, so there's our focus. All right, so we are going to draw an upward arrow half the focal length from the mirror. So that's going to be on this side of the mirror. So a convex mirror curves away from the thing you're looking at. So over here, let's measure 3 centimeters away from the edge of our mirror. That's half the focal length. We'll draw a 1 centimeter tall arrow at that point. Found a bump in the table. Let's make a good arrow. Call that object. Okay, so let's draw the ray diagram for a concave mirror together. I'm going to start off this like I did with the convex mirror. I'm going to start off the same way I did with a concave mirror. I'm going to line up the top of my arrow, my object, with the mirror, and I'm going to draw a ray that is parallel to the mirror like that. And again, I'm going to line the ruler up after that with the focus. So now my ruler looks something like this. For a convex mirror, the rays of light don't go through the focus. The focus is behind the mirror. They deflect as if they came from the focus. Reflect, probably be a better word to use. And so this ray is going to go up and to the left, like that. And then for clarity's sake, we can go ahead and just extend that ray backwards like this through the focus. I did not do a very good job of lining up my ruler, y'all. I'm sorry. That should go through the focus. And again, if you want to call that ray number 1, you can. Ray number 2 would be exactly the same as it was before. We take our ruler and we line it up with the center, like so. We draw a ray that goes to the mirror, no change there, and it reflects away from the mirror. So no change in our ruler. And so there's our ray like that. And then again, for clarity's sake, to indicate clearly where that ray came from, go ahead and draw a dashed line indicating that your ruler was lined up with the center. So make sure you draw that ray all the way to the center. Don't get lazy on me and stop short. Okay, so looking carefully, these rays of light are not going to cross. They are going to diverge forever. So I need to extend them backwards, and by showing how these lines lined up with the focal point and the center point, I've already done that. Like those rays of light extended are crossing at that point right there. So grab your ruler again. Draw your image, and then go ahead and label that image. So let's go ahead and run through the calculations and measurements on this one together. It's a little bit different than the concave mirrors. So I'm just going to measure the image distance real quick. I get like 1 centimeter. So SI equals 1 centimeter. What I need to remember, y'all, that's a virtual image. That means it needs to be negative. So SI is negative 1 centimeter. Measure the image height. And I get 1/2 centimeter when I do that. And so HI equals 1/2 centimeter, or 0.5, whatever you want to say. That would be positive. So that is an upright image. It points upwards. So the image height is positive, and it is a virtual image. So the image distance is negative. Okay, so let's actually crunch the numbers and see how our calculated values for these things compare to the measured values. So I've got some space again, like right there. So again, we can start with 1 over F equals 1 over SO plus 1 over SI. And so 1 over SI equals 1 over F minus 1 over SO. And so plugging in my numbers, I get 1 over SI equals 1 over. So our focus was -3 centimeters. So -3. And then minus, because the equation tells me to minus, the object distance, so down here, was +3. Now don't get too confused by that math. You might want to write it like this: -1 over 3 minus 1 over 3. I put the negative sign at the top so that you know it's a -1 minus a -1. And so 1 over SI would be -1 minus 1 would be -2, because that's already a common denominator. And so be careful, don't forget to invert that to get your answer. That would be -3 over 2 centimeters, or -1.5 centimeters. And so if you compare that value for SI, I got -1. I'm off by 1/2 centimeter. I did not do a very good job of drawing that blue ray. And so if I had done a better job of lining up my ruler for that first ray, let's kind of show you guys real quick, that would kind of shift that blue ray to the left. It would be less steep, and that would shift my image over to the right, increasing the image distance. And so I get a little bit less because I did not do a very good job of lining up my ruler. Now let's find the image height again. And so just like before, we had HI over HO equals -SI over SO. Solving for HI, that would be -HO times SI over SO. And so the object height, which is 1 centimeter, so negative 1 centimeter, and then times an image distance of negative 1.5 centimeters over an object distance of 3 centimeters. And so, all right, that's going to be like 1/2. Negative 1/2 times 1 would just be positive 1/2. And so I would expect a positive number because I have an upright image. If it were upside down, we would expect a negative number. All right, go ahead and hit the pause button one more time and draw situation number 5. Okay, welcome back. Let's draw situation number 5 together. Same kind of setup here. So I'm going to go ahead and, haven't done so yet, put my focus in the right spot. So there's my focus, F. This time we're drawing the same 1 centimeter tall arrow, 3/2 F from the mirror. So 1 centimeter tall arrow, 4/2 centimeters away from the mirror. So there's my object again. And let's go ahead and draw ray 1. Let's do it careful this time. Let's not make any mistakes like we did in the last one. So parallel to the mirror. And then carefully line that up. Still didn't hit it very good. Okay, so there's ray number 1. Ray number 2, we just line up with the center. And so extend it backwards, right there. And so you'll notice that those two rays are never going to cross. They're diverging from each other. So we got to look at the extended rays, and yay, they cross. And so here is my image, teeny tiny image. You'll notice again that it is a virtual image, and you'll notice that it is an upright image, just like before. So really the only thing that changes is I slide my object further away from the mirror, is my image slides a little bit to the right, but not a whole lot, and gets a little bit smaller. So one thing about convex mirrors that's a little bit more complicated is you've got more of these extended ray kind of things running around. The nice thing about convex mirrors is they kind of always look the same. Like everything kind of is just in this little range right here. And so there's a couple of good uses for convex mirrors, one of them being the fact that you can see more stuff in them. And so they're useful for things like security, where I want to see like a whole room just by looking into a mirror, like those big security mirrors in the corner. And if you look at one of those mirrors, everything is in focus because everything falls within this really narrow range of distances. And so all of our images are going to be basically in the same point, meaning I can look at the mirror and see a lot of things in focus. So try that next time you're in a convenience store. Don't rob the place because the security mirror is there. But next time you're in a convenience store, look at those little mirrors in the corners and you'll notice you can see everything in clear focus, which is very different than a concave mirror. Benefit of a concave mirror is that you can use it to like magnify things, like make it bigger. So telescopes and makeup mirrors and things like that take advantage of that. The complicated thing is that as you move the object from different positions, you're going to get very different ray diagrams. So notice that all three of these ray diagrams look different from each other. And so the diagrams themselves are not as messy or complicated as these. There's just more of them to analyze and figure out. So I will leave you guys to do all the calculations and stuff like that. I'll post solutions if I think about it, or at least the answers so that you can check your math and stuff like that. But if your math doesn't match your ray diagrams, then you should know right away that you've got a mistake and go and investigate what the mistake is. Number one mistake is just not paying attention to those signs. So what we need to remember is that if an image is virtual, it should have a negative image distance. It's on the wrong side of the mirror, if you will. If a image is inverted, like in this one, then the image height is negative. And if you have a convex mirror, we need to remember that the focal length is negative. I hope you found this instructive today. If not, please let me know. Politely, of course. If you have further questions, please let me know, and I'll see you next time. Ta-ta.